saw in the last section that an improper integral converges if the limit of an associated integral, a limit replaced with t, exists. But in some cases, it's difficult to determine whether or not the limit even exists. So the comparison test gives us an alternative approach. So we can detect convergence or divergence by comparing an unknown integral with one that we do know the behavior of. So first taking a look at this picture here, you can see that function f is smaller than or below function g. And that's all the first inequality is saying. The next inequality is saying, well, if that's the case, because an integral is the shaded area under function f would have to be smaller than the shaded area under function g. So if g is a function where we know it converges, then we also know that the function underneath is going to have to converge. So this leads to the idea of the comparison test, and importantly, and we'll come back to this is for non-negative integrals. If you know of a bigger function g of x whose area converges, then so will the area of a smaller function f of x, and that area will of course then be smaller than the area under g of x. And if your function, the smaller one, f of x, diverges, if it diverges, the area is going to infinity. So therefore, g of x, the bigger one, would also have to have infinite area under it. So it might be simpler to hear that same thing again, just said strictly in words. If the area under the larger function is finite, meaning it converges, then the shaded area under the smaller function must be finite, and that shaded area is smaller. If the area under the smaller function is infinite, then so is the area under the larger function. The only thing you have to be careful of with this test is that you don't try to automatically say the opposite of these things. So if the smaller function converges, there's no evidence that the larger function is going to converge. Or if the larger function diverges, there's no reason to believe the smaller function will also diverge. So make sure you stick to using these in the appropriate way. The whole basis for this theorem is that there's a known integral that you can compare an unknown integral to. And the tricky part of the test is knowing what integral that should be. If you think your integral is going to converge, then you have to be looking for a bigger function. And if you think your integral is going to diverge, then you have to find a smaller function. We're going to do a couple of examples of this. Beginning with example 1, does this integral I equals 1 to infinity dx over x to the 5th plus 1 converge? If so, what do we know about its limit? So this is the function that we're working with. And if you look at the shaded area under this function, starting at 1, which is here, and continuing to go, we have to decide if the shaded area is going to be finite or infinite. And we saw in the last section, you have to be really careful about trying to make a judgment from the graph, but it does look like it's kind of narrowing and narrowing. So I would suspect it converges. We're going to go ahead and proceed with that guess, but if it turns out our guess is wrong, then we're just going to change tactics, assume it diverges, and proceed that way. Okay, so our first observation is we're going to assume it's converging. The other thing we need to check, and this is again going back to the wording of this theorem, we have to have a non-negative improper integral. We have an improper integral. And if you think about substituting values from 1 to infinity, because we have a power here and we're just adding on to it, this function will never take on negative values. So we do know that this function, this integrand, is non-negative. And because of that, we can use the comparison test. If not, we'd have to come up with another tactic. Since we said this one seems to converge, we're looking for a function that's bigger than 1 over x to the fifth plus 1. Okay? So I'm going to just write, we want a bigger function to compare to. And the way that you usually begin that process is you think about the information you're given here, all right? So we're starting with the fraction 1 over x to the fifth plus 1. I'm going to think about that denominator, x to the fifth plus 1, and I want to make a simpler comparison. Very often, what you're going to do to start the process is knock off the constant, and you're going to determine what's the relationship between the basic function and the function plus 1. Well, obviously, if you take an x to the fifth power and add 1, we know the stuff on this left-hand side is going to be bigger. Now, I'm going to put the or equal to because it's certainly not wrong, but these two are not going to be equal, right? All right, so we have that relationship. Now, what happens if we make those denominators? So if we say, I'm going to put the x to the fifth plus 1 on the bottom because it looks like my integrand. I'm going to put an x to the fifth on the bottom on this side. And now what's the relationship of these two? Well, when you make things into fractions, a bigger denominator means you're dividing by a bigger number, and your result overall is going to be smaller. So these two have this relationship. And this is now going to be much easier to work with than our initial integral. Here's why. So we're integrating from 1 to infinity, and we're going to work with just dx over x to the fifth. As you saw in the last section, I can replace that infinity with a t, and then take the limit as t goes to infinity for this integral 1 to t of dx over x to the fifth. The antiderivative for this is definitely easy to deal with. It's x to the negative fifth power. So if you add 1, it's x to the negative fourth divided by negative 4. Using fundamental theorem of calculus next. And remember, this t to the negative fourth, that really means that there is a t to the fourth power in the denominator. So I really have 1 over negative 4 t to the fourth. And then over here, we have a negative and a negative, which will become positive. 1 to the fourth power is just going to be 1. So whether it's in the numerator or denominator, it's pretty much irrelevant. So we have plus 1/4. So as t increases in value, this fraction is going to approach 0. The numbers will get closer and closer to 0. And if you don't believe me, try substituting some t values. And the limit of a constant is the constant. So what I've just shown is that this integral, which represents a function that was bigger than the one I have, which remember was the goal, I've shown that this one converges, and specifically this one converges to 1/4. Therefore, since the integral that I care about, 1 to infinity of dx over x to the fifth plus 1, is smaller than my comparison integral, we've seen already that that means if this one converges, if this one has a finite area, then this one must also converge. Now the second part, what do we know about its limit? That is involving the second part of the statement. So we found a function that converges, and because our integral was smaller, it's also going to converge. Its shaded area is going to be smaller. So if we found that our comparison integral converged to 1/4, this one is going to converge, and it's going to be something smaller than 1/4. And the trickiest part of this whole process is, again, this idea of trying to come up with an appropriate comparison function. Now, to give you a little help with that, here are some reference integrals. These are integrals that are really good comparison tools. So you can see we have one for exponentials. And remember, since this says e to the negative x, another way to represent this first integral would be the integral of 1 over e to the x dx equals 1. Then we have, if you have just plain x on the bottom, 1 to infinity, that's going to diverge. And then over here, you'll sometimes hear this referred to as a p-test. Depending on the power on the x in the denominator of a fraction, again, being evaluated from 1 to infinity, if p is bigger than 1, your integral will converge. If p is less than or equal to 1, and we already just saw here where the p equals 1, then your integral is going to diverge. So if you can use something that looks like these as your reference integral, you're able to just kind of skip ahead and describe the behavior of your original integral. Here's how that's helpful. So here, as soon as I knew I had 1 over x to the 5th power, and this integral is from 1 to infinity, I don't actually have to do all this work every time, because this reference integral right here tells me if p is bigger than 1, which my p-value was 5, it has to converge, and it converges to 1 over 5 minus 1 would be 1/4, which is exactly what we found. So these integrals are going to let you take shortcuts so that you don't have to go through the whole evaluation process.